Welcome to our presentation on optimizing training for service delivery. My name is Senthooran. The co-authors and I are with the optimization group at Monash University in Melbourne, Australia. I will start with an introduction to the problem we tackled. In this work, we study the problem of training a roster of engineers who are scheduled to respond to service calls that require a set of skills. These engineers and service calls can have different locations. Our industry partner employs engineers to respond to service calls, and these engineers may be local or non-local to the job location. In the event both these options are not viable, they outsource the problem to a contractor local to the job. Hereafter, when I say engineer, I'll be referring to the company-employed engineers. When responding to a service call, the alternatives of training a local engineer, sending an already trained non-local engineer, and hiring a local contractor all involve costs. Training company-employed engineers also have the added benefit of increased quality of service, as it could lead to better response times in future service calls, as well as increase in customer confidence. In addition, costs are also reduced in the long run. The real-world data that we used in the study involves jobs and engineers in Australia. We will now look at a few simplified examples to get an idea of the problem that we tackle. In the first example, the service call is located in the state of Queensland. The options that we have here is to either use a local engineer or a local contractor, or bring in an engineer from Victoria. In this case, it is cheaper to use the local engineer. In the next example, the scenario is the same, except the local engineer doesn't have the skill to do the job. So hiring the contractor becomes the best option. If the job duration is increased to 2 days, hiring a contractor becomes expensive. Now the job duration has increased to 3 days, and the decision of training the local engineer becomes important. Making this decision is crucial, as it not only saves money, but also enables the company to provide a high-quality service to its customers in the future. However, in practice, this problem is hard to solve. This is partly because the value of training an engineer in one skill depends on other training decisions. Also, evaluating training decisions involve evaluating the schedules that are now made possible by the new skills. And furthermore, these schedules must be computed over a long time horizon. Otherwise, training may not pay off. We make some assumptions about the problem. To evaluate the training decisions, we consider an offline scheduling problem, because what we actually want to determine is how engineers should be trained, and this is a strategic decision. We make this simplification because of requirements of our industry partner. They are mostly interested in how to train their workforce rather than how to schedule the jobs, and the actual online assignment method is too complex to be replicated. We also consider that training takes no additional time, because for our industry partner, training in a new skill takes a few days and is usually only available a few times during the year. Therefore, if from a strategic point of view, we determine that it is valuable for an engineer to learn a given skill, it would outweigh any operational consideration. However, we consider the training cost, which varies based on the skill. Before we go on describing how we solve the problem, let us talk briefly about what others have done in this area. There are extensive literature on the workforce allocation problem. A significant part of the literature deals with the problem of assigning cross-trained workers, that is, trained in multiple skills to jobs that require a single skill. Cross-training allows the reduction of service delivery delays and increase the utilization of the workforce. A number of papers, like those listed here, study the effect of cross-training of the entire workforce as a single weighting parameter, but not with decision on specific skills that each staff member must learn. This approach is most suitable when the workforce is large and many staff members have the same skill profile. But in practice, the workforce has diverse skill set, and this is the case with our industry partner too. To the best of our knowledge, there aren't any other work tackling the same problem presented here. Now let's look at how we model this problem. Essentially, the optimization of training is about finding the skills that are required, that is the ones in short supply, then deciding whom to train on those skills, and finally assessing the effect of these decisions on the serving quality. Therefore, we can break the problem into three sequential steps. The basic idea is to forecast the future demand using the past data, typically over a more extended period, and determine what skills are in short supply. It is a combinatorial problem, not just data analysis. There may be enough capacity for each skill to cover the jobs independently, but no feasible assignment when considering all skills. Because an engineer can have multiple skills, the capacity of one skill is dependent on the assignment of another. The skills in short supply serve as an input to the second problem, which allocates specific engineers to train on these new skills. The skill allocation problem embeds, as a guide, a relaxation of the third problem, which assigns engineers to jobs and schedules them using their newly acquired skills. The third problem allows us to measure the quality of the solution of the first two problems in terms of travel costs and service quality. That is the delays in attending calls. Now let's look at each of these problems in detail. Capacity planning is about finding skills that are in short supply in each state to serve the local jobs with the local engineers. Usually, we use the historical data for this step. Now let's look at the involved constraints. Given a skill requirement profile, we have two main decisions to make for each location and scale. How much is supplied from the available workforce and how much is in short supply. So collectively, these values should not exceed the total required amount. Each skill supplied by the engineer should not exceed the period duration. Obviously, a skill cannot be in short supply when its requirement is zero within the planning horizon. We explicitly model this constraint. A skill in demand is allowed to be fulfilled either by existing resources or by creating resources through training or by contractors. Contracting a job means that skill is in short supply from the company's point of view. So the objective here is to minimize the cost to contract the jobs that have skill shortages and conduct training on suggested new skills. The next step is to find which engineer to train on which from the skill set identified through the capacity planning step. This is done by looking at the future service calls and by allowing travel, which means training decision considers the requirement of other states. So now let's look at the involved constraints. We restrict the set of skills an engineer is allowed to acquire to those identified in the capacity planning step. The company can set a limit on number of new skills an engineer can acquire. This may be due to budget constraints or to keep employees happy by spreading the training. In this step, we also do job allocation with a limit on number of assignments per engineer to make realistic training decisions. Remember, we do not do job scheduling here. To discourage allocating engineers to non-local calls, we apply accommodation and flight costs to interstate allocations. An engineer is only allocated to a job if his skills, including any newly trained ones, contain the skill required to do the job. The real-world data we used contains overseas jobs and engineers, but our industry partner doesn't want overseas engineers to attend jobs in Australia. So we added this constraint. When one engineer has a subset of skills of another, training preference is given to the engineer with less skills. This eliminates some symmetries. So the objective here is to minimize the cost to attend non-local jobs and train engineers. The next phase is to assign and schedule jobs. Remember, we only perform this step to validate the training decisions made in the previous steps. In this step, we include all the constraints applied in the previous step except the constraint on the number of new skills an engineer is allowed to acquire, the dominance constraint, and the constraint on the set of possible engineers who can perform a job. There are some additional constraints enforced in this step. Let's look at them now. Any two jobs allocated to one engineer should not overlap in time. We make use of the disjunctive global constraint to enforce this constraint. When contractors are not used, a limit is applied on the number of jobs with the exact skill requirement that can overlap. This is equal to the number of available engineers with the corresponding skill. Here we use the cumulative global constraint. Different jobs have different priority levels for various reasons. To facilitate this feature at the user level, we allow the input data to include a minimum waiting time for a job. So the job is only scheduled after the waiting period. Each job has a deadline that needs to be met. A job is only assigned to an engineer with the required skill or a contractor. We assume a contractor has the required skill and there is no limit on the number of available contractors. When a job is allocated to a contractor, the associated cost is applied. This cost is included in the objective function. So the objective here is to minimize the cost to attend non-local jobs and hire contractors. So the single monolithic problem is essentially modeled by combining all constraints in step 2 and 3, where the decisions on whom to train on what, allocating jobs to engineers, and scheduling are performed together. Here we omit the constraint limiting the possible set of new skills an engineer can gain. And the new objective is to reduce the sum of training and traveling costs. Now look at the experimental evaluation for our proposed approach. We ran the experiments on a machine with an Int'l Core i7 processor with a 3.7 GHz clock speed. The data that we received from our industry partner has approximately 8,800 jobs spanning over 2 years, and 10% of them are overseas jobs. These jobs are located in 22 different states and 14 of them are overseas. These jobs require 113 different skills. The workforce has 53 engineers with varying skills, and they are located in 7 different states and one of which is overseas. We model our problem using Optimising, which is a solver-independent modeling language that allows us to try different off-the-shelf solvers, both CP and MIP, on the same model before deciding on the most suitable one. To choose an appropriate solver for each step of the decompose approach and the monolithic model, we ran the preprocessing for each experiment using several solvers, both CP and MIP. The results were consistent on all occasions, and we chose a MIP solver for steps 1 and 2 and a CP solver for step 3. For the monolithic model, a CP solver worked best. For step 3 and the monolithic model, we use a program search strategy to find solutions quickly. During job scheduling, we choose the unscheduled job with the earliest start time and then fix its start time to this earliest possible time. Then we assign an engineer for that job, first trying to schedule an engineer who resides in the same location as the job, thereby favoring solutions with lower travel costs. We experimented with several search strategies and found this to be the most robust. I will summarize the results next. Please take a look at our paper for detailed experimental results. To compare the performance of the decomposed and a monolithic approach, we split the data into two: the year 1 data for capacity planning and the year 2 data to perform skill allocation and job scheduling. We use the same year 2 data for the monolithic model and the skill allocation step of the decompose approach for each period. This is to have a fair comparison. We generated 1 month and 2 month instances from the year 2 data for second and third steps of the decompose approach and monolithic approach. All the runs had a cutoff time set to 300 60 seconds except for the monolithic model, which was set to 3600 seconds. I will highlight our key observations here. Based on the year 1 data, determining the skills in short supply for each state is straightforward. And capacity planning step can find the optimal solution quickly. The monolithic model can generate better solution within its much longer time limit for some 1-month instances. Still, it scales very poorly, unable to find solutions to one-month instance and all 2-month instances. Decomposing the problem into 3 parts does restrict the resulting solutions, since the monolithic model can better an optimal solution for the decomposed problem. However, this was when we were looking at a shorter period to decide the skill allocation. From the experimental results presented next, you can see that when we perform skill allocation over an extended period, that is, when looking at the larger problem, the decomposed approach outperforms the monolithic model in terms of solution quality and solving speed. This is true for all months, including the cases that the monolithic model previously bettered. Overall, it is clear that monolithic model is not practical. Even with far more resources and solving a restriction of the problem, it cannot compete. The second experiment tackles a more practical version of the problem and is the default problem used in the tool delivered to our industry partner. Here the decisions of what skills are in short supply and which engineers to train on what skills are performed over 1 year of data. Here we use 3 scenarios to compare the effect of the number of new skills on the schedules. First is no new skills, second at most 1 new skill per engineer, and third at most 2 new skills per engineer. I will highlight our key observations here. The headline is that enabling new skill training can significantly improve the overall cost of providing the service calls. For the scenario of no new skills, 2 instances have no solutions. This highlights the need for training engineers. The savings of targeted training are significant and reduces overall cost by 30%. Interestingly, the more flexible scenario that allows 2 new skills per person does not always lead to a better overall cost. In the previous experiment, we found no viable schedule without using contractors for some instances. So we extend the step 3 model of the decomposed approach to allow contractors. The rest of the experimental setup is the same as the previous experiment. The results here do not change previous conclusions. So what did we achieve and learn out of this work? We presented a mathematical model for optimizing training for service delivery and illustrated on real data provided by our industry partner. A straightforward formalization of this problem into single model proved not to be a good one. It is impractical because of the combined complexity of the intertwined subproblems. Secondly, if the model could be solved to optimality, the training decisions that would be taken would outfit the historical data because future service requests are completely visible at training time. To avoid poor and overfitted solutions, we decompose the problem into 3 subproblems to reduce the complexity, increase the solving speed, and hide scheduling decisions from the training decisions. We model our problem using a solver-independent language, Optimising, which allowed us to try different off-the-shelf solvers on the same model before deciding on the most suitable one. We show that training optimization can deliver significant savings in comparison to the current assignment processes. So what can be improved? A potential limitation of the current approach is the use of an offline job scheduling problem for the third subproblem. While this integrates well with the first 2 subproblems, offline scheduling must give a biased measure of the efficiency with which workforce can deal with jobs. But in practice, these would be allocated on the fly. So extending the job scheduling subproblem to an online version is a more realistic representation of an actual problem, which is now possible in Menacing using a recently published technique. Once our industry partner have finished testing our system, we will take their feedback and incorporate it into the next iteration of our system. That concludes my talk, and thank you for listening.